Today we are going to discuss about RL AC circuits. AC circuit, as far as AC circuit is concerned, AC circuit can be RL circuit means having resistance and inductor only. RC circuit may be having resistor and capacitor only, and RLC circuit, the circuit may be having resistor, inductor and capacitor together. Now, considering the RL circuit here we are having a resistance and inductor. The voltage across resistance, let it is VR, the voltage across inductor, let it is VL. When AC supply is connected having VT is equal to VM sin omega t. The current flowing in this circuit, it will be IT, then which is having Im sin omega t plus minus theta. Here, because here it is inductive, then it will be minus theta. Now, considering the waveform of this resultant circuit, if this is the waveform for voltage, this is the waveform for current. Because this circuit is neither purely resistive nor it is a purely inductive circuit. If it was purely resistive, then current and voltage both were in same phase. If these were purely inductive, then current and voltage were in 90-degree out of phase. But it is having resistor inductor both. That is why current and voltage, this if it is a 90, it will be lying between 0 to 90. Let it is the having some angle of theta. Now the waveform of current will start after this angle theta, because in case of inductive circuit current lags. If it is a purely inductive circuit then current lags by pi by 2. Now because the angle is between 0 to pi by 2, let it is theta, and hence it is starting after theta. This is the waveform now for current, because the power is the product of current and voltage at this instant. During this period voltage is positive whereas current is negative, the resultant power will be negative. During this period, then voltage is positive, this is the voltage value, this is the current value, both voltage and current both are positive, the resultant value of power will be positive. Then again in this period, for this period this voltage will become negative whereas current is positive, the resultant value of power will be negative for this period. As the case of purely inductive circuit, this positive and negative half cycle of power were equal, but in this case the positive and negative half cycle, positive and negative part of this wave is not equal, and hence we can say in case of RL circuit always there is a power consumption, but in case of purely inductive circuit there was no power consumption. Drawing the phasor diagram, since we know the applied voltage is V, the RMS value of this instantaneous value is, let it is V, that V is the current flowing in this circuit, let the RMS value of this current is I. Because these two elements are connected in series, the current in these two is I, the common value is current, let current is taken along the reference. The voltage drop in resistive component, it will be in same phase with current, because this is due to the resistance only. The voltage drop in inductor will be 90-degree, leading the voltage, leading the current, and in other words we can say current is lagging by an angle of pi by 2. This is the voltage across the inductor, and hence the VR, if we are taking the resultant of this VR and VL, the resultant value will be V. Resolving this component, this component will be real component, whereas this component will be imaginary component. This is imaginary component. Now considering this resultant function, let if it is a current in the circuit, if it is the voltage applied in the circuit, then there will be a phase lead or lag between, because current lagging the voltage. This is the phasor for current, this is the phasor for voltage. If we can say voltage leads the current by an angle of theta, or current lags the voltage by an angle of theta. Now, for the complete circuit, V is equal to I into my Z. Here, Z is nothing but the impedance. Impedance is the combined effect of R and L in RL circuit. Now, is the opposition offered to the flow of current due to the combined effect of resistance and inductor. This is impedance. Impedance is represented because we know in this function, if this is I into R, this is I into my xl. If these two vectors, this is I into my z. If these three vectors in this triangle is divided by I, then we will be having this is r, this is xl, this is z. And resolving this component, then we can write in notation, phasor notation. Using phasor notation, z will be equals to r plus jxl, because xl is above this reference axis, and hence it is taken as plus here. Now z will be iz will be equals to ir into, now multiplying this these three vectors by I, then it will be I into my z, it will be I into my r into my I into my xl, I into my z, I into my r, I into my xl. This I into my z is nothing but v, this I into my r is nothing but vr, this I into my xl is nothing but vl. And hence this relationship what was for impedance, resistance, and inductance. Similarly, the voltage relationship across inductor, impedance, resistance, and inductor can also be realized as V is capital V applied voltage must equal to the VR plus JXL, or the phasor sum of VL and VR. Now, again, applying the concept of power, power is equal to current into a voltage. If it is instantaneous value of current and voltage, then we can get instantaneous power as a function of time. It is Vm sin omega t, Im sin omega t minus theta. Here minus is taken because current lags the voltage by an angle of theta. But now multiplying these two functions and simplifying, then the resultant value of P will be equals to this. This is also a instantaneous value. If we want to find out average value of this function, then we have to take integration over the period 0 to pi, integrating this function over to 0 to pi, and then simplifying, the resultant value will be equals to Vm Im by 2 cos of theta by 2. This component will again simply after simplification will become 0. Then the resultant value will be this one Vm by root 2 Im by root 2. Then it will be Vrms Irms into cos of theta, or simply V into I into cos of theta. In electrical engineering, there is a special significance of cos of theta, and this is known as power factor. Now, from these three phasors here is voltage across resistor, voltage across inductor, and voltage across the complete combined effect of resistor and inductor can be resolved in phasors, in phasor representation. If we are considering the phasor of V are in same phase with I, the phasor of VL is 90 degree out of this I, then the resultant value V can be represented as V is equal to phasor sum of these two quantities. Now the phasor sum of these two quantities, considering this triangle, from here let it is A, B and C. This A, B, C triangle is nothing but the voltage triangle. This is known as voltage triangle. If we divide these three vectors or phasors by I, then it will remains only R. Here it will remain only XL. Here we will be having Z. Then this triangle, this equivalent triangle is known as impedance triangle. Now for this voltage triangle, instead of dividing the vector phasor by I, then if we are multiplying this I for these all these three vectors, then it will be I into my VR, this is I into my XL, then it is I into my V, then I into my VL, this is VL. This is I into my VR is nothing but the power P, the I into my VL is power Q, then I into my V is power S. Here these three powers P, Q and R, P, Q and S. P is the active power here, Q is the reactive power, and S is the apparent power. Now, considering these three powers, if resolving this component as a triangle, then in a phasor space and time, then we can say Z is equal to R square plus XL square from this Pythagoras theorem. Similarly, we can apply Pythagoras theorem for power. PS is equal to P square plus Q square under root, and hence we can realize that there in this in electrical system there are three type of power: P, Q and S. P is the active power, also known as true power, and real power. Now, active power and reactive power. The unit of active power P is equal to VI cos theta is kilowatt or simply watt or megawatt, depending upon the magnitude of the quantity. Then the Q is the reactive power, which is given by V into I. Here, this V and I are the RMS value of voltage and current. Sine of theta. The unit of this is kilo VAR or simply VAR, volt ampere reactive. Whereas the third case is S is equal to V into I. The unit of this is VA, and here V is the voltage, A is the current. Now, considering P and S, P is VI cos theta, S is V into I, then dividing P and S, then we can simply calculate cos of theta. Cos of theta is equal to P by S. VI will be cancelled out, then we will be having a cos of theta. Cos of theta is known as power factor of the load, and angle theta is the power factor angle. Now, from these three triangles, theta can be analyzed according to the quantity used for these individual triangles. Now, considering the phasor diagram, the angle between cosine of angle between current and voltage phasor is known as power factor, or simply it can be written as cos of theta, where theta is the angle between current and voltage. Then cos of theta from the impedance triangle can be represented as cos of theta is equal to R by Z. Since we know this is R, this is XL, then the resultant value is Z. This angle is theta. Resolving this component, we can find out cos of theta. Then the third triangle is power triangle. In case of power triangle, again we are having three different powers. This is P, this is Q, this is S. This angle is theta. And from here we can say cos of theta is equal to P by S. And hence the power factor in this electrical system can be defined in three ways: using phasor diagram, using impedance triangle, and using power triangle.